So this is all about the factor and remainder theorem, and it turns out this is stuff that we've already stumbled across when we tried to do synthetic division and synthetic substitution. But today we're going to formalize it and give it a name. First we'll talk about the remainder theorem. The remainder theorem says that if we have a polynomial and we divide it by something that looks like x minus a, in other words, there's the coefficient in front of the x is a 1, the remainder will be the constant f of a. Now, this kind of notation here, that the remainder is f of a, that's something new, so we're going to try to verify that we agree with that. Again, I think it's something that we've already seen before. So what exactly does this mean? Well, if we take, here's an example polynomial, f of x equals all this. It'd be great if you could pause the video and copy the f of x down, and then copy all of this down, and then we'll go ahead and we'll get started. Okay, I'm hopeful that you paused and you copied this down. Now, what we'd like to do is we'd like to take this function and we'd like to divide it by x plus 2 as an example. In other words, f of x is going to be divided by x minus a. In this case, it'd be x minus a negative 2. And so we want to then see what is the result we get. Now we're going to use synthetic division, so I'm just going to copy down the coefficients. So 3, 2, negative 5, 1, and negative 2. And then I'm going to put a little bar down here and a little box over here. And I'm hoping that you remember what to put in this box over here. Why don't you go ahead and pause the video and see if you can remember that, and then in a second we'll all get back together and we'll see what we need to put in this box. Okay, hopefully you figured out that you're going to put a negative 2 in there, and that negative 2 is the number that we substitute in for x to make this guy 0. Okay, so that's what we're looking for, is a negative 2. Now we're going to go and do the math, and we're going to go ahead and see what the remainder is, because this whole remainder theorem is about if we divide a polynomial by x minus a, the remainder is blah blah blah. So we want to see what the remainder is. So here we go. So I'm going to go ahead and do 3 plus nothing is 3. Let's go ahead and change color. It's 3, and 3 times negative 2 is negative 6. And 2 and negative 6, negative 4. Negative 2 times negative 4 is 8. 8 plus negative 5 is 3. Negative 2 times 3 is negative 6. Negative 6 plus 1 is negative 5. Negative 2 times negative 5 is positive 10. Plus negative 2, we get 8. So the remainder here turns out to be 8. And supposedly, that's what we get if we did f of a. And in our case, a is going to be, let's see, it's x minus a. So again, let's go ahead and write this out. In our case, it's x minus negative 2. All right, there we go. Our a is negative 2. And so what we expect is that the remainder will be equal to f of negative 2. Now, let's just go and verify, just to be sure that that really is true. So I'm going to do f of negative 2, and it'd be great if you did it at home yourself. In fact, I'd love for you to do it. You're going to do just like I do, put in the parentheses, put in the negative 2, and try to evaluate. Let's see if we get the same result. Now, I'm asking you to try this at home without watching me do the work, because you can use the practice. I would love to see you get this right on a test, and it's really hard to get this correct on a test if you haven't been practicing it yourself. So I'm going to go ahead and plug in the negative 2, negative 2, negative 2, negative 2. You're going to pause the video and you're going to go ahead and try to calculate and see what that turns out to be. Okay, hopefully we're back, and let's see here. This is going to be negative 2 to the 4th power. That's like 16 times 3. By the way, it's positive because it's an even power. So that'll be 48. This will be a negative number because to the 3rd power. It'll be negative 8 times 2, so that's minus 16. This will be 4, positive 4 because it's squared, and times negative 5, so minus 20. And then finally plus negative 2 times negative 2 plus 4. So let's see what we get. 48 minus 20 is 28. Minus 16 is 12. Aha, I just realized I made a mistake here. When I got down to here, I wrote minus, I thought this was -2 times -2, but really it's x minus 2. So it's -2 minus 2. So this should really be -4, not +4. That'll get me a better result. So 48 minus 36 is 12. 12 minus 4 is 8. So sure enough, f of -2 is 8. And it turns out that this helps us to verify that, yeah, if we take a polynomial and divide it by x minus a, the remainder will be f of a. It'll be f of the -2 in this case. And this is something that we already saw when we tried to do synthetic substitution. Is that that when we plug in a number here, the remainder that we get is the result if we evaluated this function. Okay, let's try let's take a look at another rule. So this next theorem is called the factor theorem, and again, it's something that we've already basically seen before, but here it is stated officially, is that if we believe that the binomial x minus a is a factor of the polynomial f of x, then f of a must equal 0. Now again, it's harder to understand with letters. Let's look at an example. So again, I'd like you to copy down the function you see, and then write out the division problem, and then let's go ahead and do the division and see what we get. Because if x minus a is a factor of f of x, that means that we must be able to divide f of x by x minus a, and we should be able to divide evenly. So let's go ahead and give that a try. Let's go ahead. Hopefully you'll pause the video and write this all down. Now let's go ahead and pick up. We're going to use synthetic division, so I'll do 3, -1, -62, -40. And over here we'll put a box. And in that box, hopefully you know that we will be putting a -4 in here. And so again, we're back to this idea that the a here must be a -4. X minus a -4 is the same as x plus 4. So let's go ahead and evaluate. And when we do 3 plus nothing is 3. -4 times 3 is -12. -12 plus 1, -13. -4 times -13 is +52. -62 and 52 is -10. -4 times -10, +40. That gets us 0. Okay, now in this case the remainder was 0. The remainder is 0. And what we do now is we have to rely on the results from the first video, because in the first video what we said is that if I plug this value of a in here, that this remainder over here is going to be equal to f of a. Let me go back and let's just take a look just to remind you. Remember, the remainder itself will be f of a. So if I take a and plug it in here, the result that I get here should be equal to f of a. So all we're doing is saying, hey, if we plug it, oh, this is the thing we're expanding on. In this first one, when we did divided by x plus 2, since we got an 8 here, x minus a is not necessarily a factor because we have a remainder. Since we have a remainder, we can do the division, but this guy's not a factor. In this case, since we got f of a equals 0, we can say x plus 4 must be a factor. So this is kind of a powerful thing. is that if you're trying to graph a function and you plug in numbers like -1 and -2 and -3 and -4, and you evaluate this guy over and over again, and for one of those numbers you get a 0, we can say for that number, if we do x minus that number, that will be a factor that we could evenly divide this polynomial by. And it'd probably be worthwhile to actually see what happens. By the way, since we did this as synthetic substitution, you may remember it's also synthetic division. So this guy right here must also be a factor if this is a factor. So let's go ahead and write that out, what we actually get. This should actually be 3x squared minus 13x minus 10. And so supposedly x plus 4 times this gets us this. And so this guy itself must be a factor. Now, it turns out this guy itself is factorable, so we're going to try to factor. I'm going to go ahead and add a little bit onto your body of knowledge, or at least I'll remind you of how to do the x factor. We do 3 times -10, that's -30. Again, you can pause the video and work ahead in case you want to see if you remember how to do this. It'd be great for you to test yourself. Consider this test review. In the meantime, if you started playing again, here I go. I'm going to put -13 down here, and then I'm going to make a list of all the factors of 30. And I'm going to try to find two numbers that add up to -13 and multiply to get -30. Might be 2 and 15, could also be 3 and 10, and who knows, maybe could even be 5 and 6. No, not 5 and 6. 3 and 10, if I put 3 here and 10 here, I'd have to make this minus, and they don't multiply together to get me -30, so it cannot be that. So it must be 2 and 15. So I'm going to put 2 here, 15 here, make the 15 negative. Now, I am going to show you something new. In the past, we had this technique where we divided by 3 and divided by 3, and then we reduced, and then we made these into the factors. And if you like that method, that's great. Go ahead and use it. But I'm going to show you a new method, and if you like this one, feel free to use it. I'm going to use the box. And the way the box works is like this. I'll use the 2 and the -15. I'm going to rewrite this as 3x squared plus 2x minus 15x minus 10. So what am I doing? Well, -13x is the same as 2x minus 15x. And I use the 2 and the -15 here to find those two numbers. Other than that, I'm just using the 3x squared and the -10 as you see them. Now I'm going to fill them in this box here, and let's see what happens when I do. So I'm going to put 3x squared here, and then I'll put 2x and minus 15x. These guys are always going to be diagonal from each other, and then I'll put minus 10. And what I'm going to do is I'm going to kind of factor out the GCF from these two. Looks like it might be an x. And I'll factor out the GCF from these two. Looks like it might be 5 or minus 5. I'm going to try minus 5. And then I'm going to go ahead and factor out the GCF from these two. Looks like it might be something like 3x. And then I'm going to factor out the GCF from these two. Looks like it might be something like maybe minus 2 possibly. Could be plus 2, minus 2. Now we double check and multiply. X times -2 is not that. So this must be plus 2x. There we go. And, or I'm sorry, this must be plus 2, because x times 2 gets me 2x. 2 times -5 gets me -10, so that works. 3x times -5 gets me -15x, and 3x times x gets me 3x squared. So it turns out that this guy should look something like this. It should be x plus 4 times x minus 5 and 3x plus 2. Now, I want you to know that I'm going way above and beyond the factor theorem at this point. All we said is that if x minus a is a factor, then f of a will equal 0. We could have stopped right there. What I wanted to show you is that if you know that x plus 4 is a factor, you can then divide this guy and find additional factors, and if you do, we can use zero product property to solve and find all the solutions to this polynomial. So in this case here, with these three factors, we just use a zero product property. So x is going to equal very simply -4 and +5. And this one's a little trickier. Maybe you might want to try 3x plus 2 equals 0 and then go ahead and solve this linear equation. 3x equals -2, x equals -2/3, something like that. And so we'll go and say these are the solutions. Ooh, don't forget the negative sign, -2/3, and then I'll go ahead and box that as the answer. That's all the possible solutions. And by the way, I want to point something out else that's kind of interesting here, is that there's 1, 2, 3 solutions, and this happens to be a third degree polynomial. That is no coincidence. It turns out that when the degree of your polynomial tells you the maximum number of roots that you can have. Now, sometimes some of your roots will be complex. They don't all have to be real like this. But if I have a third degree polynomial, I can expect 3 roots. If I have a fourth degree polynomial, I can expect 4 roots. If I have a second degree, a quadratic, we can expect 2 roots for sure. And sometimes the 2 roots are real, and sometimes the 2 roots are complex, and sometimes, yeah, so I'll leave it at that. Okay, that's all I got to say for the factor and remainder theorem. Hopefully this has been helpful.